the Bohr model is specific to hydrogen. Yes. Okay. All right. So, sorry. All right, so let's work with hydrogen a bit more. The reference sheet that's on your desk, it's like a colorful paper. Look for the Bohr model on it. It's got the concentric rings. So, and I'm going to come right back to this because that's our quantum model we're going to talk about. So, looking, you should see this. Yeah? Find it? Yeah. Okay, there's a, Benny, there's some reference sheets right behind you. Could you pass them up to the girls in the front of your row? They're right, your hands are on them, yeah. Sorry, I got a bunch of stuff back there. So pass them up this way. Who else needs a reference sheet? Okay, that's good. Just pass them up and you guys can spread them around. All right, so you can see on here it says the Bohr model measured in what? Measured in what? Nanometers, right. So making sure that you remember nanometers are not usable in the speed of light formula, you must convert to meters. So you can see the labels as well. So let's look at, sorry, I saw I'm writing from first period. Let's look at a drop from n equals 4 to n equals 2. N equals 4 to n equals 2. Tell me what wavelength that correlates with. So basically what you're doing is, I'll do one example here with you. Looking at n equals 4, it's going to be this ring. So follow it down till you find the dot. Okay, there's a dot there, there's a dot there. But you also want to go dropping from n equals 4 to n equals 2, so you need to have the drop fall to this orbit here. So you are concerned with this drop from here down to n equals 2, which is here. So when you follow the line, I know it's kind of tedious. When you follow the line, ooh, what did I do? Okay, when you follow the line down here, you can see it correlates with what wavelength? For what? 486, because if you drop down right here, it correlates with 486. What color of light do you think that is? It's right smack in the visible range. In the middle of where you live, right? So maybe greenish, bluish. But if you really want to double check, look at the very bottom of the Bohr model, because it goes through EMS spectrum, like more specifically about the waves, and then it has a chunk and expands out the visible light. So 486 nanometers correlates to how many meters? 486 nanometers times 1 meter, 10 to the 9th nanometers is 4.86 times 10 to the negative 7th meters. So what color is it? Blue, right at blue, right? So it is right between, no, like, it's more on the blue side of things, right? Question? To the actual Bohr model. The Bohr model is right above this, and what we did was we said from n equals 4 to n equals 2 was a drop that was from right here up to this one, and we followed that line down to see what wavelength that correlated with. So let's do another one. Yeah.
Also, like an electron doesn't orbit.
It does orbit. It can orbit, but the hydrogen ion or atom has one electron and that's it. So it can exist in the excited states, and as it goes into the excited state, it must fall back down. It has no choice. So it shows the different transitions it could undergo. This is still somewhat of a lie, but we use the Bohr model a lot in honors chemistry. We use it less so as you go to upper levels, because we know more, that's all. Okay, so let's do another one. Let's go n equals 5 to n equals 2. So tell me what wavelength that correlates with. 434, and if you go down 434 and you look down the visible light spectrum, it's going to fall right, on the violet side of the blue, so it's going to be like right in here. 434 is a 4.34 times 10 to the negative 7 meters. So you can use this tool, but I really just want to go through how to use the tool, because if you get this on your test and you're like, I have no idea how to use this, it's useless, right? It's just a piece of paper. So the tools, and this is the reference sheet you will get on the end of, not end of course exam, NC final. Okay, we don't use this all the time, but we're going to use it as we need to throughout the year. So we're going to learn how to use this answer key in disguise, because it's really an answer key in disguise. You just have to know how to use it. Yeah. Yeah, because I went from nanometers to meters, and that's the conversion 10 to the 9th. So it skips the decimal over backwards, or 9 decimals. So I just do it in my head because we just do this a lot. So it's 10 to the negative 7 meters. But you'll notice that as we go over to the radio wave side, it's going to be larger. So if you get to draw it, it would be like huge long wavelengths and then really shorter. I'm not really supposed to be changing the amplitude, but I am. And as you get shorter. So you know the indirect relationship between frequency and energy as related here. And I think, I'm sorry, frequency and wavelength. I thought it was written down here. I may have lied. It's not written there. Okay, let's go through and let's do a couple examples. Just shout these first ones out, okay? So, what happens when an electron jumps from a lower energy level to a higher energy level? Does it emit or emit or absorb energy?
Oh, wait.
What do you think?
Absorb.
Right, because you're going to take it from, this is my analogy. Nucleus is mom, okay, positively charged. Electrons are crazy teenage boys, half of you. You're close to mom, you're grounded, pretty stable, pretty chill, don't do anything crazy. This can also be teenage girls, okay? I don't know many of you girls that are this crazy, but really good. So when you're close, you're nice and stable, nice and low energy. Don't tell mom all the crazy stuff you do. But when you're out here, La La Land, out here at the excited state, you are frantic, energetic, crazy. You're not grounded. You're high energy. I don't know, crazy is the best word for that. So the farther away from the nucleus, the higher energy you are. So you had to absorb energy to get up to that state. Hyped up on caffeine and sugar. Yeah.
Well, if you're not grounded.
You're not grounded, I know, because you're like, mom's not holding you down to the nucleus. Okay, higher energy level down to lower energy level, what happens? Emits or releases, those words are equivalent. Okay, so now tell me what wavelength is equivalent to a transition from n equals 4 to n equals 2. Look on your sheet.
I didn't get the sheet.
N equals 4 to n equals 2. There are those some extra sheets. Where are those sheets at? Are there any extras? Look right there with keys then. That's where you have buddies. Anybody? 486. There, I think I know we didn't do that. Okay. All right, so if you get the 486, you've used your tool, you've looked at the transition, you follow the line down. You could tell me that's about, whatever we said, bluish light. Now, if I asked you to give me the energy of that, how would you do that? Sam, tell me what you got. If I wanted you to get energy. I believe in you. Anybody on that side of the room? Nick? Thank you. You've got to convert this to meters first. So 1 meter, 10 to the 9th nanometers, gets you 4.86 times 10 to the negative 7 meters. All right, so we have currently wavelength. I like to recognize what variable it is, because then the formulas start to pop out in your head. Gage, what formula am I using next? I only have wavelength. I can't plug into a formula that doesn't use my variable. I hear you. You're saying E is equal to HV, yet I'd have nothing to plug in there.
So then you have to do the speed of light.
Thank you. So you got to use the speed of light formula to use this first to get what? Frequency. Thank you. Okay. So you got to connect the dots for yourself. C is equal to lambda times frequency. To solve for frequency, you must do C over lambda, 3.00 times 10 to the 8 meters per second over 4.86 times 10 to the negative 7 meters. Meters and meters cancel. That's some number of hertz or seconds to the negative 1, right? So after this, you would then do what? You have your frequency. You do what? Plug it into the other one. So E is equal to 6.626 times 10 to the negative 34th joule seconds times the frequency. And that's going to get you energy, which is measured in what unit? Joules. And that should cancel the seconds that are in the joule seconds, that little bitty seconds over there, should cancel with the per second notation on the frequency. Okay, so I'm not gonna do a ton more of those because you guys have a problem set you need to ask me questions on for that. Questions on our two formulas we're using for the rest of our lives? No. Okay. Let's talk EMS some more. This is oops, sorry, you can't see that at all. This is one more practice with EMS, and I think that most of you guys are very mathematically minded, very quantitatively minded. We need to work more qualitatively as well with the conceptual understanding. So I've talked a lot, but I want to see what you guys can do by yourselves. the POGIL worksheets are always very model-based, and they show you images and they show you data. They say conclude from this or glean from this data what you can. So I really like them for the conceptual understanding. You're only going to do questions number 1 through 23 on there. There's like 28. So, and anytime it says draw, don't have to draw or color unless it's like a project, okay? So don't worry about drawing or coloring. And then on the worksheet, I'll pass them out just a second. You guys won't probably be able to read this table very well because it's a little tiny worksheet. So this is 10 to the 8th, and you can see obviously this is the speed of light associated with all the light waves. So as you go down, you guys can scroll this up and down. But at the bottom, I have some more of the images that are just kind of difficult to see on the worksheet, and the wavelengths at the end. So that will probably take you guys about 20, 25 minutes to do that worksheet. It's just a quick reminder of everything we talked about yesterday. Somebody adopt Nick, okay? Because he wasn't here. And then after that, it's independent work time. Independent work time is a treasure, okay? You need to use it wisely. And that's something that's just basically, I'm trying to let you guys work with the people you need to work with, ask me questions if you need to ask me. So first thing I'm going to do is give back your test again. I have the multiple choice sitting in the back. You guys will grab whatever color and go through that. And I will show you how I calculate test grades, just in case I put something in the grade book wrong, or you just want to see how I grade things so that you can understand your success in chemistry. And then after that, if you ask me some questions, you are required to look at your test for 5 minutes. I did have somebody make 103. I understand that person will look at it for about 5 seconds. But that's okay. Work on the carbon fiber research, and I'll answer questions there. And then if you need some help with citations, APA or MLA, don't care. I'll help you there. And then after that, if you have some time, work on your Problem Set 5. But Problem Set 5 has 2 pieces to it. EMS stuff we learned about yesterday and today, and then electron configurations, which we're talking about tomorrow. So you're only going to be able to do about half to 3/4 of the problem set. So make sure that you don't try to do things that you're like, I have no idea what I'm doing. It's okay. So I will say, I'm gonna let you guys do this for a little bit, and I'll come back and do quantum. Okay? But unless you want to do quantum now, and I'll leave you alone for the rest of the class. Vote. Quantum now? Quantum after you do some stuff. That was a great vote. Let's try this again. Quantum now? It's only going to take me about 10 minutes. Quantum after you do some stuff. Okay, I'll do quantum now. It's a democracy. I'm good with that. These are the notes from quantum. Looks like this. It's on your EMS. No, it's on your notes you were writing on yesterday. Looks like this. We're going to on this side right here. Okay, cool. So this is following up with Schrodinger's theory. Jade and Tyler. Okay, this is following up with Schrodinger's theory. Basically, we want to now go into the deep details of, do we know exactly where electrons exist? Kind of yes, kind of no. Because the Heisenberg principle, do you guys remember Heisenberg? Not from Breaking Bad, but from your reading guide 5. Heisenberg's uncertainty principle. You can either know the location or the speed of an electron, but you cannot know both. So, Mr. McNeil told me this joke. I'm going to see if I can not murder it here. Heisenberg and Schrodinger are driving down the highway, and they get pulled over. The police officer says, do you know how fast you're going? And they said, no. And he said 108 miles per hour. They said, darn it, now we're lost. They can't be able to keep in where they are. Okay. Come on, guys. All right, so anyway, Schrodinger. Some of you guys are actually like, oh, okay, let's move on. Okay, so Schrodinger is going to now go into more details about where the electrons are, but sometimes we still don't know their exact location, so we're going to kind of call them orbitals or neighborhoods, like I like to call them. So he agreed with Bohr. He said they're quantized, because Bohr said the energy levels, or orbits, he said they were quantized, aka has a specific set amount of energy. And Schrodinger was like, yeah, I pretty much agree with that, but I think there's more to it. Dude, they don't move in specific orbits. They move in these kind of more locations and general locations. They don't have a specific set path they have to travel in. So he does not define a specific path or orbit like Bohr did. He says they're free to just kind of move around in these general clouds of electrons. So his postulates are more about, I think I can find an electron in this area, but we know a lot more information about it because we don't know the exact location. So it's more about the probability of finding an electron in an electron cloud. The electron clouds come in lots of sizes and shapes. And you guys saw some of those when your presenters were showing you their models. So their shapes and their sizes and what the electrons are doing there all have numbers associated with them. It's almost like an address for electrons. An address that kind of narrows down like the general location, not the exact house, kitchen, filled with a knife. Okay, we're not going to know exact everything, but we are going to know a lot of information. So it kind of describes the electron configurations, which we're going to talk about tomorrow. So these are called the quantum numbers, numbers that tell us about the quantum mechanics of the model. So the first quantum number is called the principal quantum number, but nobody calls it the principal quantum number. We call it the N number. Where did you just see N number? Or what was that correlated with? The energy level. The energy level was just simply the orbit or the distance away from the nucleus. So the principal quantum number, it sounds really fancy. It's literally how far it is from the nucleus. So n equals 1 is closest to the nucleus, n equals 6 or infinity as farthest away from the nucleus, right? And obviously, if you kind of think of it as concentric rings still, kind of like Bohr did, you would say the energy level and the distance from the nucleus. As you increase the distance from the nucleus, it's going to increase in size because it's just taking up more space in general. So we do have that kind of general appearance of increasing in size. So that's what N stands for. The next one sounds real funny. Angular momentum quantum number. Nobody calls it that either. We just call it the shape of the neighborhood that the electrons live in. So they're also called sublevels. Sublevels are kind of like the shape of the neighborhood of where the electrons exist. And they come in 4 shapes. They're theorized to come in more shapes, but we haven't discovered that much yet. So we've got this down so far. The first shape that the neighborhood can be shaped as is a sphere. Sphere is called S. That makes sense because the sphere starts with S. Okay? So the next shape of the orbital or the sublevel or the neighborhood is going to be called P. It does not look like a P. This is what it looks like. It's like a double dumbbell, 2 balloons. Okay? So that's called P. P can come in different varieties though. P can go up and down. What axis is that lying on? The y-axis. So I can go up and down, that's the y-axis. If I go this way, it's the x-axis. And if I go out of the board, it's coming at you. Yeah? It's like 3D. And going into the board, that's what axis? Z-axis is this way. All right, so the S has one variety. That's it. It's a sphere. Can you do a sphere in different orientations? No. Any way you look at it, it's still the same orientation. It's a sphere. The P's come in 3 different orientations. They can be this way, or this way. So that's just what the P looks like. There's just a dumbbell. The D shape is a double dumbbell. I'm going to draw it here. Double dumbbell. And I'm not going to draw every single D orientation because it's kind of complex, but it can be either like on the Y and X axis, or Y and Z axis, or X and Z axis, or it's got a funny donut shape to it. I'll show you that on the next page. So these neighborhoods just have different shapes. That's all I'm showing you so far. The last shape, so this is called D. The last shape it can take on is F shape, which is flower. And it's got kind of a overlay of 3 to 4 orbitals. It also comes in different shapes, but I like to just focus on this single one because it doesn't look like a flower. Yeah. So sphere, S. Single dumbbell is P. Double dumbbell is D. And flower shape with lots and lots of orbitals, lots of different locations on the neighborhood. That's going to be F. So this is just getting more complex because we're talking about quantum, so we just have to be able to understand a little bit of this because it is relevant in tomorrow's discussion. Okay, so the last 2 descriptors here are still kind of narrowing down exactly, like if I wanted you to find electron number 20 in zinc, you would have to tell me, oh, well, it's in the 3rd energy level, and it's in the P orbital that's oriented in the x-axis, and it's the one that's spinning this way. So that's all I'm doing. You're just kind of narrowing it down. And it's there, but you don't know exactly where in the orbital. So then the last part right here, this quantum number, magnetic quantum number, is talking about the axis that it's taking on. So that's why I drew those other ones over there. So you can just really specify you're in the x, the y, or the z axis. And then the last part here is that the electrons, 2 electrons together. What happens when they're together?
They will both
They repel. They do not like to be near each other, okay? But if they have to live in the same neighborhood and they have to live in the same orbital, they have to deal with it. So the way they deal with it is they spin different ways. Because if they spin the same way, they create a magnetic field that makes it makes the element less stable, or the atom less stable. So they prefer not to spin the same way, because they're just spinning, they're vibrating the whole time. So if they spin opposite ways, also known as clockwise or counterclockwise, then that helps. So we can actually narrow down, we think this electron's spinning clockwise, or we think this one's spinning counterclockwise. I don't write clockwise and counterclockwise, I just draw an arrow up or an arrow down. That's how I denote something spinning up or down, clockwise or counterclockwise. Yeah.
Every atom has like every kind of orbital,
Does it have every what?
every kind of orbital.
No, hydrogen only has sphere. As you go down to like zinc, it's going to have spheres, dumbbells, and double dumbbells. As they get bigger, they get more orbitals because they need more space to hide all their electrons. Smaller elements have like just spheres or just spheres and dumbbells. Okay, so we're going to talk about that a lot more tomorrow. But we got your basis. All right, we have an hour left in class. Okay, 25-ish minutes on the EMS worksheet, which I'm going to pass from the back here. We got right on these, por favor, Mrs. Tashes. Not that way. Oh, okay. I'm just gonna. Okay. They're coming around. I did not do this in a very organized fashion. Okay, so the lab stations, I'm going to clean off some of them, but you guys are free to go about the lab stations, and I'll pull back up the images, and you guys can also work on independent stuff after you finish your worksheet.
Is this still up?
That is the worksheet. Lab is tomorrow because we do this catch a lot of times. 1 through 23, please write on your own paper. Worksheet?
Are we sure?